And welcome to this video on enthalpy of chemical reactions. We've talked a lot about enthalpy or heat and how heat is transferred and how we can actually account for the amount of heat or enthalpy in a physical process, and now we're going to actually take a look at chemical reactions. We've done a little bit of this before with the amount of energy released through exothermic reactions with combustion and using some conversions, and now we're going to take a look at how we might be able to do this using a couple other methods. And so over here in this diagram you see that we have possibly some sort of a reaction of interest here to go from some A to D. Okay, so we start here and we end here. And so a lot of times we might have information about how to go from A to D directly, and other times we might have to actually go through a couple smaller steps. So we might have to go from A to B and then B to C and then C to D, and actually the amount of energy, if we account for all three of those, should equal the same amount of energy here. And that's what we refer to as Hess's Law. So we're going to talk about Hess's Law today and standard enthalpies of formation and how we can actually determine what's going on in a chemical reaction. So grab your Cornell notes and let's go ahead and get started. So the first thing is just what is Hess's Law? And so we have this thing that's called Hess's Law or Hess's Law of heat summation. And really what we are looking for is the ability to take two or more thermochemical equations, and if you remember, those are balanced chemical equations that have some sort of an enthalpy value attached to them. And we can add those to get a final equation for a reaction. And so this is those going through a couple of smaller steps in order to get to the overall net equation. Okay. And once we've done that, we can take the total of the enthalpies of reaction for that one that we're interested in, and we can find that by adding up all of the thermochemical reaction equations. So why would we want to do that? Well, we have a couple possible reasons. One is some of our reactions of interest are very, very difficult to measure. Maybe they're really, really slow, or they're just a difficult thing to measure, so we can measure subparts of that. And the other thing is, if you remember back to our reaction mechanisms, a lot of reactions take place in smaller steps or in multiple small steps. And so we can actually take each one of those multiple small steps and kind of divide them out separately. And we should get the same thing. So here's actually an example of how to calculate using Hess's Law. And so our question is, what is the enthalpy of reaction or heat of reaction for this reaction up here? Okay, so let's take a look at this reaction overall. So here's our reaction of interest that we want to find out about. Okay, and in order to find this, we're given reaction A and we're given reaction B. And what we need to do is we need to figure out how to make reaction A and reaction B add up to equal reaction, the overall reaction that's up here. Okay, now when we do that, it's kind of like creating taking the pieces of a puzzle and making them fit what the front of the box looks like, which is this one up here. And so we're going to manipulate a couple of things. The first thing that I need to do is I need to take a look and find something that's in each one of these reactions that I only find on one side of the reaction of interest. So if I take a look, I see that this is actually found, but this one is found on the product side. And so I'm going to underline the C2H4O right here, and I see that it's found over on this side. And so I'm going to have to do something with this in just a moment. And then let's take a look down here. Well, I see that I have the C2H5OH, and I have that same thing up here, but I have a different amount of them. And so what we're going to do is we're going to make these fit one another. So this one is a reactant in reaction A, but it's actually a product in the thing that we are looking for. And so what I need to do is I need to flip this reaction, okay? So, and I actually write this next to it. I say I'm going to flip this reaction, which basically means I'm going to take this reaction and write all of these things on this side as my reactants. And these ones over here are going to now be my products. Okay, so if I flip this reaction, I also want to flip the sign. So if I flip the reaction, I'm going to flip the sign. And this now becomes a positive enthalpy. Okay, so we're going to have a positive enthalpy there. All right, now in the next one, remember we said that we have this one and it's in the same place. So this is a reactant in reaction B and it's a reactant in the reaction of interest. But you see right here we actually have two of these and we only have one of them here. So what I'm going to do is I'm going to multiply reaction B times 2. Okay, and if I do that for the reaction, so that means I'm going to put a 2 here. 2 times 3 gives me 6. 2 times 2 gives me 4, and 2 times 3 gives me 6. Okay, so I multiplied this whole thing by 2. Now what I do to the reaction, I also have to do to my enthalpy. So now I'm going to multiply my enthalpy times 2. It's still going to remain negative, but now I'm going to multiply this number times 2. And when I do that, I get a negative 2,734 kilojoules. Okay. So now this is my delta H when this is multiplied times 2. Now you can actually go through and add up all of these to see that this works its way out. And that when you have the overall net equation, you end up with this. I'm not going to actually do that. I'm going to assume that I've done that. I will, if you would like me to do that in class, I'll go back through and do that for you to show you that when I add these two equations up now, they actually give me this equation right here. Okay. Sometimes that can be a little bit challenging to figure out. So what I want to do is I want to take and add my two delta H's in order to find what my heat of reaction is. So delta H of my reaction is going to be equal to the positive 2,385 kilojoules plus our negative 2,734 kilojoules. And when I do that, my delta H of reaction, my enthalpy of my reaction, is going to be a negative 349 kilojoules. So there is my answer. Like I said, we can actually go through and add both of our equations up to get this overall equation. I'm going to assume that what I changed here would do that, and it actually does. Okay, so we're going to take a look at one other method, which is using standard enthalpies or heats of formation. And with standard heats of formation, these standard heats or enthalpies of formation, we have a new little symbol, but remember, again, it's just delta H, so don't freak out because there's a couple other symbols there. It's still just our enthalpy. These are going to be our enthalpy values at standard state, which is 1 atmosphere and 25 degrees Celsius. They're elements in their standard state and have a value, or elements that are in their standard state have a value of 0. Okay, and the values can be found in table 17.4 on page 580 of your textbook, and I will also have a handout for you in class that you will have to be able to work through these. And the overall idea is that, and now in order to find our enthalpy of our reaction or our heat of our reaction, we're going to take the sum. So this symbol here means the sum of all enthalpies for our products minus the sum of all enthalpies of our reactants. And so we have to find the sum of each one of these, and then we subtract them, we find the difference between them. So a big question is, well, why would we do this? There's too many reactions to know or to look up or to do Hess's Law for every single reaction type that's out there. And so what we can do is we can use this to actually have one list for heats of formation that can determine many different heats of reaction easily, or as many as we have enthalpies of formation. Okay. So let's take a look at an example then. So I've already obtained all of these. Now, one of the things is that these states of matter, when we're doing this, are very important. There's a difference between heats of formation for things that are in the gas, the solid, and the liquid state. And so when you're looking into your handout or the table in the book, you're going to want to make sure that you have the right one of those. Okay. So I've looked at these values already, and so what I do a lot of times is when I go to do these, I'm going to go, okay, what are my heats of formation for each one of these? Okay. So for H2S in the gas form, I looked this up and it is a negative 20.5. Okay. And that's kilojoules, so all of these are in kilojoules. Now, for fluorine, it is actually going to be 4 times the formation for fluorine. So we're going to take 4 times the formation of just making F2 gas. Now, F2 is one of those elements in its standard state, and so it's 0.0. There's nothing to that one, and so this is the value, okay? Over here, we're going to take 2 times our HF, and HF is going to have a value in the gas form of negative 272.5. Okay. And then finally, for our SF6, it is going to be, there's only one of them, and so it's going to be a negative 1,220. So all of these values, okay, these delta H values that we have come from either the table in your book or the handout that I will give you. We also have to remember that we're multiplying them by the coefficients. So these numbers that are in front are the coefficients that we're multiplying them by if there's more than one of them. Okay. So once I have all of these, what I want to do is I want to figure out my enthalpy of my reaction. To do that, I'm going to take the sum of my heats of formation of my products minus the sum of my heats of formation of my reactants. So I see that my reactants are over here and my products are over here, and so I want to separate those out. Okay. So I'm going to make my products will be the green ones here. Okay, those are going to be my products, and then we'll make the pink my reactants. So these are my reactants here. All right, so I want to just line these up. So in order to solve for this, my heat of reaction is going to be my product. So I'm going to have my 2 times my negative 277, or excuse me, 272. Lost part of that 2 there. So 2 times negative 272.5. Plus, because remember, it's the sum of, so the sum of, we're going to add our negative 1,220. Okay, so this is going to go here. So this bracket here. Okay, and then I'm going to subtract from that my negative 20.5 plus 4 times 0. So again, we have these ones here, and we have these ones here. Okay, I'm almost running out of room down at the bottom, so let me see if I can get this to work for me. So in order to solve for my heat of reaction, okay, when I added these two up, I ended up with negative 1,765 kilojoules. Okay. Put those in brackets, and I'm going to subtract from that the negative 20.5 that I get when I add these two together. So negative 20.5. And when I get that, I end up with a negative 1,744.5 kilojoules. And that is the enthalpy value for this reaction using heats of standard heats of formation. So I hope that was helpful, and we will try some practice problems when we get back to class.